Hello and welcome back to MD3. This time we are still on linear operators, but now we are progressing to more complicated stuff. We will be using Riley, Hobson and Bence, sections 8.2.1, section 8.3 and 8.4. So there's a lot of material which I'm going to cover, but I'm not going to cover everything. I do want you to, as always, this goes without saying, you do need to look at section 8, look at the sections, actually read them, and understand the material from both my lecture notes and these sections. So we are going to do quite a bit now, and we're actually going to work towards matrix multiplication and matrix addition. Alright, so let's get here. So the very first thing we're going to look at here are the basic properties of linear operators. And the first is that if you have linear operators A and B operating on a space, on vectors in a particular space, then the linear operator A plus linear operator B operating on X is equal to linear operator A operating on X plus B operating on X. Now I put a star here because this only works if A and B transform X into the same space. Now think about it. If A was a rotation operator and B was a projection operator, which lost the dimension, then when A operates on X, it will maintain the dimension of X. It's not changed. So if X was two-dimensional, then A operates on X and gives you a two-dimensional vector. But if B was a projection operator, you would lose a dimension. So there could be problems associated with loss of dimension. So I put a star here, just keep that in mind. Then we have the second of these properties is that if you multiply an operator by a scalar, remember a scalar is a complex number, it belongs to the set of complex numbers, then that's the same as operating with A on a vector and then multiplying the result by the complex number. And the third is that if you have two operators A and B, now this needs to be you've got to be careful here again, so I should put a star there. Then the effect of operating with A and B on X is the same as operating with B first and then operating with A. Okay? So those three are the three important properties. Now in general, operators do not commute. So operating with A and B on X is not the same as operating with B and A on X. Now once again, let's think of a simple an example as to why this might be the case. Let's say B was a rotation operator and A was a projection operator. Then B rotates X and you get something which belongs to the same space, and A then projects it, let's say, onto one of the axes. If you now use A first, well, A projects X onto one of those axes and then B rotates. Now if you draw some diagrams, I think you can convince yourself that these two orders give you a different result, and it's a good exercise to show yourself that this actually happens. Then we have the null operator, O hat. O hat operates on any vector X in the space and gives you a 0. Now this should tell you already that the matrix form of O hat has to be the 0 matrix, a square matrix with zeros everywhere. Then we have the identity operator, which we've seen before when we looked at examples of linear operators. I hat operates on X to give you X for all X in this space. And the identity operator we have seen has the matrix form as a diagonal matrix. It's a square diagonal matrix with ones on the diagonal. Now if A hat operating on X is equal to B hat operating on X for all X in this space, then A hat is equal to B hat. Now this might seem like this is an interesting, in fact it leads to a direct question. How do you test, an identity holds for all X in a space? Well, you can't test every single vector in a space. But what you can do is to realize that if you show it to be true for all the basis vectors in the space, then because any vector in a space can be expressed in terms of the basis vectors, therefore you have shown it to be true for all vectors in the space. And we'll use these ideas when working through some examples, but you need to think a little bit more, think ahead as to what do these things actually mean, how do we deal with them. Then we come to the inverse. If there exists an operator which I will call a hat minus 1, such that a hat minus 1 when operating on a hat gives us the identity operator, and which is also equal to a operating with a hat minus 1, that means they commute, then this operator a hat minus 1 is known as the inverse of a. If an operator does not possess an inverse, then it is said to be singular. Now what about, are there operators without inverses, and what do they have in common? Now let's think about it. If you have a rotation operator, it rotates, the rotation operator takes some vector and rotates it into another vector. Well, you can always rotate back, right? I mean, there's nothing to stop you. If you can rotate this way, you can rotate that way. You just rotate by minus the angle we rotated that way. So the rotation operator is almost definitely has an inverse. But what about the projection operator? So what about the projection operator? If you've got an operator, a vector here, and I'm going to draw another vector here. All right, and let's draw an axis system. Now, if I project, then let me just get this. Yeah, if I project the blue vector, I will get a blue vector down here. Let's not, okay. That's the projection of the blue vector down here. Now if I project the red vector, then, oops, I didn't mean to draw an arrow, but it doesn't matter. Let's just draw it properly. If I project the red vector, I will get the red vector which happens to be identical to the blue vector. They project to the same vector, which means if I apply the projection operator, it takes in fact an infinite number of vectors and projects them onto any given vector in the projected space. Here I'm projecting on this axis. There are too many things to keep track of here. So this would be the E1 hat axis, for example. I'm projecting both vectors onto the E1 hat axis. Now, there are an infinite number of vectors which project onto the same axis, onto the same result, which means that if I wanted to do an inverse, it's impossible, because if I was given one of these vectors on this E1 hat axis, I wouldn't know to which of these should it go. In other words, we've lost information here. Now I'd like you to think of other examples of singular operators, because a singular operator will not have an inverse. You won't be able to go back once you've operated with it. I'll leave that as an exercise for you. Okay, now we move on. Basic matrix algebra. We are now in Riley, Hobson and Bence 8.4. It appears like we have skipped 8.3, but we haven't. 8.3 contains some basic information about matrices, which I'd like you to look into on your own. So 8.4. Now what happens, what Riley has done now, Riley, Hobson and Bence have done now, is to take these properties of operators, these three are boxed up here, and to use the matrix expressions for each operator to write down matrix and matrix vector identities. So what is the matrix expression you're going to be using? Let me remind you. So this is a reminder. If we've got the operator A operating on X to give me Y, then the matrix form of this is y is equal to a matrix multiplied by x. Now to get to the matrix form, let's remind ourselves, you have to introduce a basis. For both x and y, you need to introduce a basis, and when you do that, you will get the matrix form. Okay, so that's just a reminder. Now when you do, when you convert, so use the matrix form for each of these expressions, then you end up with matrix identities shown here. Now I'm not going to prove 1 and 2, I want to leave that for you. I want to prove the hard one, that's 3. Now that's the reverse of what would happen in quite often in school and colleges. You know, someone proves the easy ones and it leaves the hard one for you. Here I'm going to do the other way around. Okay, so let's have a look at number 3, which is, I'm going to have to show this. So how do we begin to show number 3? So we look at property 3. Now let's write down property 3 here. It stated that if you had operators a and b operating on x, that's the same as operating with b on x first and then operating with a on the result. Now, in order not to complicate things, I'm going to assume that there is no change in space when a and b operate on x, and then I will work off very quickly the more general case. So we're going to assume the following. I'm going to draw it down here. Let's start with a vector space V of dimension n. This is the dimension row, and this is the basis. And so here's my basis. Okay, so we've got a vector x which belongs to this space. Now what happens is we operate with the operator b hat. B hat takes, that means what we've done here is we have b hat operating on x, and that's going to give me another vector y. Okay, now remember I said that we want to keep the space the same, so b hat simply takes a vector from here and does something like the rotation operator, for example, and you get back a vector in the same space. So y belongs to the same space, which means the dimension here is still n, the basis is still e I hat, and that's the same space. I should have drawn a long equals, so that's equal to y. All right. Now what's going to happen is this result, this y, is going to be operated on by a. So we'll draw another arrow here. Now we have the operator a acting, and it changes. Remember, nothing is changing any space, so this space remains the same. Dimension n, ei hat, basis is the same, and now a operates on y, long equals, to give me a z. So that's what we mean here, is these things are operating in turn. So if I wanted to write it down directly, then z is equal to, sorry, that's a horrible equals, but I hope you know what it means, is equal to a operating on y, and y of course is b operating on x. That's what z is. Let's write it down slightly differently. That's a bit awful. Okay. Now what I want to do is to convert each of these steps into a matrix form individually and then show that this results in this. Now in this expression here, I have used different dimensions, m and n. In what I'm going to derive here, I'm going to keep the dimension the same. Everything is going to have dimension n. So the assumption here is no change of space. Okay, and that's why the space is the same everywhere. So now let's have a look at this. When B operates, the first equation we want is we want to tackle is y is equal to B operating on X, and in matrix form we write this as the vector column vector y is equal to the matrix B. It's now going to times X. Let's put some dimensions down here. X is an n-dimensional column vector. Because the space hasn't changed, y is also an n-dimensional column vector. So B has to be dimensions n by n. It's a square matrix. All right. Now we have the other equation. Z is equal to A operating on y. That's here. In matrix form, the column vector Z is equal to the matrix A operating on, multiplied by the column vector y. Now y has dimensions n, Z has dimensions n because it is the space hasn't changed. We made the assumption that the space stays the same. Therefore A must be an n by n matrix. Alright, so we've got these dimensions of these matrices in here. Now we need one more bit of information before we can go on. See, the operator A times the operator B is another operator. It must be, after all. So let's call it C. And we're going to make use of that. So there's one more bit of information we need. Call I don't know what C is, but I don't need to know what C is. What I need to know is what C does to any vector X. So C operating on X, what does it give me? Well, this is the operator C, and it gives me Z. Therefore, in matrix form, and if I put it the other way around, so I have them in this form here, therefore Z is equal to the matrix C times X. Now X is dimension n, Z is dimension n, so the matrix C must have dimensions n by n. Alright, let's have a brief pause here. Alright, we now know the dimensions of all our matrices, the dimensions of A, B, and C. C is, remember, the matrix of A times B. They're all n by n, and they're n by n because we have assumed that the dimensions of the spaces don't change after these operations. We now need one more thing. We need to write down the basic equations for the operators acting on the basis vectors. So let's remind ourselves of what this is. The basic equation says that, whoops, I have a phone call, let me pause that. Okay, sorry about that. It looks like we get disturbances even while trying to make recorded videos. Okay, so let's get back to what we were trying to do. We've just worked off the dimensions of all these matrices are n by n. These are all square matrices. So now I want to find out, and now we want to prove this relation, number 3. For the special case when the dimensions of the spaces are not changing, the spaces are the same. Okay, so for that we need our basic relations. The basic relations tell us how these operators A, B, and C change the basis vectors of the space. So let's remind ourselves, when an operator A operates on E hat I, we get the sum j goes from 1 to n. Remember, the dimension says the same, so it's still n. And we have A j I E hat j. Now this also is the same for B. So b hat operating on ei gives us j is 1 to n b j I e j. And the same for c. The c operator is a composite operator, which is the result of operating with a and b. Because all these operators are operating in the same space, they all behave the same way. There's absolutely no change here. So c hat operating on ei hat gives us c j I e j. All right, so now let's start with this equation, and we're going to use these index these basic equations, but instead of x here we're going to have ei. So let's start with that. Oops. So it's operator A, operator B, and ei is equal to, we have to show, I mean, we are told that this is the same as a hat b hat operating with ei. All right. Now what we're going to do, here's the strategy. The strategy is that, so this is our starting point. We're going to show that this identity results in that matrix equation for any of the basis vectors. Now because it happens for all the basis vectors, it must be true in general, and that's what we're going to do here. All right, so let's start with the left-hand side first. So the LHS is equal to a hat b hat ei hat, but remember a hat b hat is the same as, by definition, it's c hat. So this is equal to c hat ei hat. Now we know what c hat does to ei hat. It gives us this. So that's equal to the sum j goes from 1 to n cji e hat j. All right, so that's the LHS. Now let's work with the RHS. The RHS is this thing here. So it's a hat operating with the result of b hat operating on ei. Okay, so that's going to be a hat operating on, now b hat operating on ei is here. It's the sum, j goes this thing here. Let's put that down. It's going to be bji ej. All right, and now this is a linear combination of vectors. Now remember, a linear operator is called a linear operator because when it operates on a linear combination of vectors, it's the same as the linear combination of a hat operating on each of the vectors in turn. So this means we can pull out the sum. So that's a short way of saying it. Pull out the sum. bji is a scalar, it's just a component, and then we have a operating on ej. Now let's see what a operating on ej is. Here we are. A operating on ei gives us this. So a operating on ej, well, just replace I with j, but then call j something else. I'm going to call that, I have a j here, so use a operating on ej as the sum k goes from 1 to n, oops, a k j e hat k. All right, so that we get a double sum. I love double sums. J goes from 1 to n, bji, then we have the sum k goes from 1 to n, akj, and then we have an e hat k in there. All right, so far so good. Now let's see what we should do. I'm going to interchange the sums. These are finite sums, so we can do it without any concerns. If you had infinite sums, you can't always do it. I'm going to put a parenthesis there. 1 to n. And let's rearrange stuff. I'm going to put the a first, kj, b, j, I, and then we put the e hat k on the outside. Now what I'm going to do, and you'll see why in a minute, is in this expression here, I is not summed over. So I is not a dummy index. But k and j are dummy indices, which means I can call them what I like, what I want to, as long as it's convenient. Now let's have a look at what we're going to do, right? We're going to make this left hand side equal the right hand side. Now on the left hand side we have a sum over j, and then we have an e j hat here, and there's the I and here's the j. Now what I'd like to do is to make this outer sum a sum over j. Well, that's fine, I can do that. Just interchange j and k. Can you do that? Of course you can do that, because j and k are dummy indices. I could call them whatever I want, as long as I don't mess them up, understand, you know? So interchange, so let's write this down. Because j and k are dummy indices, interchange them. We can interchange them. So we're going to do j interchanged with k. That means the right hand side is equal to, where we had a sum over k, we're going to have a sum over j, 1 to n, parenthesis, this becomes a sum over k, 1 to n, a kj becomes a jk, bji becomes bki, and e hat k becomes e hat j. And now compare with LHS. Now if you look at the LHS, which is here, we see that this coefficient cji must be equal to the stuff in the parenthesis. Cji must be equal to the sum k equals 1 to n a j k b k I. Now what is c? C is the result of operating with a and b. So what we are actually saying then is that the composite effect of operating with a and b is this thing here, or dot a times b in matrix form ji is equal to the sum over k ajk bki, or in more conventional form, I'll interchange I and j because I like having I first and then j. So the ijth component of the product of two matrices A and B is given by the sum k goes from 1 to n aik bkj, and that is our matrix multiplication formula. Pictorially, what we have done is the following. A times b, pictorially what we have done is, let me just draw these things here. I'm going to pause it and then draw it and then come back. Okay, I've just drawn these matrices out, and they are square matrices. They are all n by n. What we have said here is that in the C matrix, any one of these terms, C11, is going to be the first row of A times the first column of B. So C11 is equal to A11 times B11 plus A12 plus B21 plus all the way to A1n plus Bn1. And that's what this expression means. Now, what I'd like you to do is to, write down this expression explicitly, let's say for a 2 by 2 matrix, for 2 by 2 matrices. Convince yourself that applying this algebraic expression is the same as multiplying two matrices row times column, as you have probably learned how to do. And this is the way matrix multiplication works. So let's take one more case. If I wanted to have this term, so the C21, then I need the second row, which is this one here, times the first column, which is again this one here. Yeah, that would give me this term here. All right, now before ending, I want to at least motivate. Now this is getting to be too long a video, so I'm just going to motivate the general case. In the general case, when you operate with these operators A and B, the space changes. So let's see what I mean by that. I'm going to draw this here and then, so pause the video and then come back. Okay, now to the general case. Now I'm going to go much faster, and you're going to have to bear up with this. So in the general case, we start with a vector space V of dimension n with basis ei as before, and a vector x resides here. But when B operates on x, we get a vector y which resides in a different space, V prime. It has dimension m, a basis fi hat. Further, when A operates on y, you get another vector z which now resides in yet another space, V double prime. It has dimension L and basis gi hat. Now this is the most general case you can have. Okay? And then we have a composite thing. If you consider if you define C to be the net effect of A and B, then C takes you directly from V, the space V, all the way to the space V double prime. Okay? Then B hat operating on EI gives us a linear combination of the basis functions of the prime space. That's in terms of the Fi. A hat operates on the Fi's, because A hat operates on this space to get to the double prime space. A hat operates on the Fi to give you a linear combination of the G hat case. And finally, C operates directly on the unprimed space and takes you to the double prime space. It goes from the EI basis to the GI basis. So C operates on EI to give you a linear combination of the G basis. Now we do exactly as we did before. Start with A and B operating on EI, which is the same as A operating on the result of B operating on EI. The LHS is equal to C operating on EI, which is equal to this sum in terms of the G basis. The RHS, we first write what the effect of B on EI is. That gives us a sum of the F basis. That's here. Now A operates on the F basis. This is the linear combination of vectors, so A can be brought in, and A operates on each of the F basis vectors to give you another sum in the G basis. And when you change indices and fill in the steps, and this I'm going to leave for you, you can then show by comparing the left hand side and the right hand side that Cij, which is equal to the matrix product A times B, the ij component of that, that's given by the sum over K of Aik Bkj. Now this looks the same as what we had before, except that where we had an n, now we have an m, And the dimensions of our matrices they are not square matrices anymore. If we start with, so let's remind ourselves of these dimensions. The starting one has dimension n, then we go to an m dimension, and then to an l dimension. So this sets the dimensions of B. B is n to m, A is m to l, and C is directly n to l. So C is equal to A times B, C is L times n in dimension, A is L times m, and B is m times n. Now there's a rule here. If you look at the dimensions of C, its left and right hand dimensions are the same as the left and right hand dimensions of the product. And the innermost dimensions of the product have to be the same. Otherwise you can't multiply these two matrices together. Okay? And that's a sort of general way of matrix multiplication. Now look at Riley, Hobson and Bence, because there will be more things explained there. Now I'm going to leave you with one puzzle. We have not really shown equation 3. Equation 3, just to remind you, is this one here. In equation 3, we're not dealing with a basis vector ei or ej. We're dealing with any vector. This is the component of any vector x. We haven't really shown equation 3. Now how do we go about doing it? I'm going to leave this to you, but I'm going to motivate it. First of all, read Riley, Hobson and Bence. But more importantly, let's write x in terms of its components and the basis vectors, the ei's. Now operate with both operators, the a, b, which is equal to the c operator on x, and first the b and then the a on x. So if you look at just c operating on x, c operating on x is the same as c operating on the sum of the components of x times c operating on the basis vectors. C operating on each of the basis vectors gives you a sum of the C matrix times the G basis. Why? Think about it. Look at the diagram above. And then when B operates on X, it takes you from the E I hat basis to the F basis. I haven't put those steps here. Then A operates on the result, and then you're going to compare the left hand side and right hand side and show that number equation 3 holds. Okay, it's quite a long exercise, but it's definitely something you should do, so I'm going to double star it. If you have questions, if you're getting stuck, then this is the kind of thing which we need to deal with in the tutorial session. Alright, so you must work on this, and any problems, we handle them in the tutorial session. That's it now, for now, so thanks for watching, and that's where we end.